We've all felt the warmth of the sun on our skin. This heat doesn't reach us through the vacuum of space by any conventional means. It travels as radiation, a fundamental process in the universe. Thermal radiation, to be precise, is the emission of electromagnetic waves from all matter with a temperature above absolute zero. Yes, everything around us, from the icy rings of Saturn to the glowing embers of a fire, constantly radiates energy. We just don't always see it. At everyday temperatures, this radiation falls primarily in the infrared spectrum, invisible to our eyes. As an object heats up, its atoms vibrate more vigorously. This increased motion translates into more energetic radiation. Eventually, the emitted light shifts into the visible spectrum and we begin to perceive a faint red glow. Think of a blacksmith heating iron until it glows red hot. Further heating pushes the emitted light through the rainbow of colors, from orange to yellow, then to white, and finally to a bluish white at extremely high temperatures. This change in color reflects the increasing energy of the emitted photons. Stars, for example, exhibit a range of colors based on their surface temperatures, offering a glimpse into their internal furnaces. Our ability to detect this radiant energy has revolutionized our understanding of the cosmos. From studying the faint afterglow of the Big Bang to probing the atmospheres of distant planets, thermal radiation provides a window into the universe's most fascinating phenomena. Thermal radiation arises from the very essence of heat. Heat, in its most fundamental form, is the internal energy of a system due to the motion of its constituent particles. These particles, whether atoms or molecules, are in constant motion, vibrating, rotating, and colliding with each other. This internal energy can be increased or decreased through various processes such as heating or cooling. When a body loses internal energy, its particles slow down, and this lost energy is emitted as electromagnetic radiation. Conversely, when a body absorbs radiation, the energy of the incoming photons increases the internal energy of its constituent particles. This continuous exchange of energy through radiation is a fundamental aspect of how the universe works. Imagine two objects at different temperatures placed next to each other. The hotter object will emit more radiation than it absorbs from the colder one, leading to a net transfer of energy. This transfer continues until both objects reach the same temperature, a state known as thermodynamic equilibrium. Thermodynamic equilibrium is a crucial concept in understanding thermal radiation. In this state, there's no net flow of heat between objects, even though they continue to exchange energy via radiation. Imagine two objects facing each other, both painted black. They both absorb all the light that falls on them and radiate energy according to their temperature. If they're at the same temperature, the energy they absorb will be equal to the energy they emit. This balance ensures that their temperatures remain constant despite the ongoing exchange of energy. This principle is vital in various fields, from astrophysics to engineering. For instance, understanding the equilibrium temperature of a spacecraft exposed to solar radiation is crucial for its design and operation. Similarly, predicting the temperature distribution within a combustion engine relies heavily on the principles of thermal equilibrium and radiation. To fully grasp the complexities of thermal radiation, physicists often use the concept of a black body. Now, a black body isn't some exotic, invisible object. It's an idealized physical body that absorbs all incident electromagnetic radiation, regardless of frequency or angle. Picture a sphere, hollowed out and painted black on the inside. Any light entering this sphere through a tiny hole bounces around inside, getting absorbed with each reflection. It's essentially a perfect absorber of radiation. While no real-world object can perfectly replicate this behavior, some materials come close. These materials are crucial in various technologies, from solar panels designed to absorb sunlight to specialized coatings used in telescopes to minimize stray light.